Hypothesis testing for the mean, 7.3, where sigma is now unknown. Big difference between 7.2 and 7.3. Now sigma is unknown, okay? If sigma is unknown, what would we use instead? We would use S, the sample standard deviation, okay? So instead of using the standard normal distribution, the Z curve, okay? Because with the Z curve, I would use sigma. We instead use the T distribution with degrees of freedom n minus 1, okay? So remember, S and T go together, all right? S is the sample standard deviation. Z is the Z distribution, the standard normal, which uses sigma. T distribution uses the S, okay? So in order to do this, we must have a couple things to be true. Number one, sigma needs to be unknown. If sigma is unknown, all right, we're on our way. We're using the T distribution. Number two, we got to have a random sample. And number three, the sample needs to either be population normally distributed or n greater than or equal to 30. Okay, n greater than or equal to 30. Remember, the T distribution, as n gets larger and larger, the T distribution becomes more and more normal, okay? So the normal distribution is what the T distribution is converging to. Now, one thing to note, okay? One thing to note here. Let me see if I can make this smaller. Okay, there you go. To get the T, I do x bar minus mu over S divided by the square root of n. Literally the only thing to do to get this that's different than the Z critical value or the Z score is the standardized test statistic is instead of dividing by sigma, I divide by S. Okay, so S is, we replace sigma with S. Now the number of degrees of freedom, if it's not in the table, remember we use the closest number in the table that's less than the value needed. So just to give you an example, to remind you, say I get a degrees of freedom, maybe n is like 59. Well, degrees of freedom is n minus 1, so the degrees of freedom is 58. But when I go and I look up the table, okay, so when I go and I look up the T distribution, I go down my degrees of freedom. The problem is I don't see a 58. I see a 50 and I see a 60. So I use, what does this say? It says use the closest value in the table less than the value needed. So if 58's not in there, I can't use 60, I use 50. And so I would use this row right here, okay? So my degrees of freedom would become 50. So the DF is equal to 50 here, right? Just to help you out. All right. So finding critical values with the T distribution, it's a little bit different than with the Z, all right? So the first one I'm going to do the left tail test. Left tail. Now with the left tail, okay, this is where I am going to say if I'm a left tail test, I'm on the left side here. I'm shading. So my critical value T0, my alpha, all right, my alpha is right all in this tail, shade to the left. So what do? I use one tail alpha column. There's only one tail alpha, all right? With a negative sign. With a negative sign. All right? So to give you an example, find the critical value T naught when alpha is 0.05 and when n equals 25. So I want to find the critical value here. So 0.05 and n equal to 25. So how do I read this? I'm using the 1-tel alpha level, okay? So 1-tel alpha level right here. And then I am told that the alpha is 0.05. So I'm going down this row here, or this column. And then what do I want? I want n equal to 25. N equal to 25, n minus 1 for degrees of freedom. N minus 1 is 24. So I go to the 24 row, and my answer, 1.711. Now, the problem here the problem here is that this is a positive. So if I wrote this out, it would be like 1.711 over here. But we know it's a left-tailed test, so what do? I put the negative sign in front. So the critical value, T naught, is negative 1.711. So what does this mean? If this is my critical value, T naught here, okay? If I get a T that's smaller, so T, a standardized test statistic T that's less than the 1.711, what do? I reject the hoe. Okay? Now, instead of being a left-tailed test, maybe it's a right-tailed. Right-tailed test. Okay? As always, what's in the middle? 0. Right tail is on the right side. This is a positive T naught. So I'm still going to use the 1-tel alpha because there's only one tail for a right tail. There's only one right tail. Okay? With a positive sign. So you can put a positive sign here, or you can just leave it as T naught. I mean, you think about it, you don't ever write +5, you just make it 5, right? So you don't have to put the positive in front, but you know, if it makes you feel better, go for it. Okay, so what do I want to do? I want to find T naught given alpha 0.01 and n equal to 3. If n equals 3, that gives me a degrees of freedom of 2. Okay, so let's go look it up in our chart. Uh-oh, wrong one. So let's see. All right. So 1-tel alpha 0.01, that's this right here. So I'm on this column here. Now n equal degrees of freedom equal to 2, that's right here. So go to the 2 row and go over 6.965. Okay, 6.965. 6.965. So T naught is 6.965. Now this is on the positive side. Okay, that was on the negative side. So what does that mean? If I get a value as extreme or more extreme, what do? Any T values over here, so T's greater than T naught, which for this one is 6.965. What do? We reject the hoe. Okay. So my alpha over here is all in 1-tel. The last test is the 2-tel. The 2-tel test. What am I going to use? I'm going to use the 2-tel alpha. How about that? Doesn't it just spell it out for you? So the 2-tel alpha with a plus for the right side and a minus for the left side. Okay, so your answer is going to be a plus minus. So here's what I want. I want to find T naught, okay, and negative T naught for alpha 0.05 and n equal to 10. If n equals 10, the degrees of freedom is 9. 10 minus 1 is 9. So I want an alpha on the left and an alpha on the right. In the middle is 0, so I've got a positive T naught over here and a negative T naught over here. So something as extreme or more extreme over here and over here. Okay. So how do we do it? Go to our table. I want alpha 0.05, 2 tell, so this is bottom row right here. 0.05 alpha, that's right here. So it's this middle row. And then n equal to 10 gives me a degrees of freedom 9. So I'm looking, all right, 2.262. 2.262. So T naught equals 2.262. Now it's a positive 2.262 over here, but it's a negative 2.262 on the left side. Okay, so if I get a T that's smaller, so a T that's less than negative 2.262, or I get a T that is greater than 2.262, then I reject the hoe. Okay, so those are the scenarios for getting your critical values. So you don't have the option to use the p-value that you got to in the last section for the t distribution. The only way we can solve this is by comparing critical values with the standardized test statistic in the rejection region. Okay, unless you have a calculator that calculates this for you, you're gonna have to use the table and this method for left, right, and two-tailed tests. Okay, so make sure you know what's going on for these tests, these 3 different tests. All right, here's your one example for how to work through it. Anytime we have a word problem, first thing I do is I go and I look at the numbers. MP3 player 3, that's not really a number that matters. Oh my goodness, my country accent messed this up. Mine is mean. Sorry, Google. So Siri got me messed up there. The mean battery life of MP3 player is at least 30 hours. So the first number I have, at least 30. Now when I see at least 30, and I've got a mean at least 30. So how does at least 30 relate to the mean? All right, I could have an average of 30 or more. So greater than or equal to. Okay, the company says is my claim. All right, so my claim, that's what the company claims. Since it has equality in it, it's the hoe. The hoe is the equals. What's the opposite of the hoe? It's the ha. What's the opposite of being greater than or equal to? It's less than 30. So now we have it set up. What type of test do we have? I look at the ha to tell me the test. This tells me that it's a left-tailed test. It's a left-tailed test. So I'm going to be using this one right here, okay? Left-tailed test. All right, so what do I do here? What do I do? Well, before I jump into this, I need to make sure that I can drive the Ferrari, okay? So you suspect that they're lying. So what do? You go out and you get a random sample of n equal to 4, all right? You go out and you get a random sample n equal to 4. That's what that number tells me right there. And then you find that the mean battery life for that sample is what? it's 28.28. So X bar, for the sample, for that sample that you just went out, you got 4 iPods, you test out the battery life, the average was 28.5. And then it says a standard deviation of 1.7. Now you might be tempted to say sigma equals 1.7, but why would that be wrong? Because you don't see anywhere where it says population standard deviation. It only says it only says standard deviation. It doesn't say population. And when it doesn't say population, you have to assume that it's S. And look, guys, it's talking about the sample. The sample, you find the mean here and a standard deviation here. So from the sample of 4, we get this information here. Is there enough evidence to reject the claim at alpha 0.01? Alpha 0.01. So in order to use this, we have to know CLT. CLT says random sample. We know it's a random sample. It's told us it's a random sample. But it also needs to be n greater than or equal to 30 or normally distributed. We don't know anything about the population, so we don't know it's normally distributed, and n is equal to 4. So we can't do the problem. Not enough info. Done. All right? Pretty easy, right? Now, let's do my alternate scenario where I know the population is normally distributed. Okay? So if I know that the population is normally distributed, then what? Then I can use my test. Okay? Then I can use my test. So what do? Find the standardized test statistic. T equals x bar minus mu over S divided by the square root of n. So x bar 28.5 minus mu 30 over S 1.7 divided by square root n. N was 4. Okay. This number, if you type it in the calculator, you get negative 1.765. Okay. However, we need to compare it with our critical value. So we need to find the critical value and identify the rejection region. Okay, this right here was find the standardized test statistic. Z or T rather. Okay. Now to find the critical value and identify the rejection region, we got to use this technique here. Okay. So what do we need to do to find that? We need to know N, which was 4, so that means degrees of freedom is 3. And we need to know alpha. Alpha for this problem was 0.01. What type of test is it? It's a left-tailed test. So I know I'm on the left side of a left-tailed test, so that's a negative t value. Okay? So go look it up. Degrees of freedom 3. Alpha, it's a 1-tail. It's only on one side. If I go look that up, I get negative 4.541. Okay? Now, what's my decision? If I find a value that's more extreme than this, some t value more extreme, what do? If it's less than 4.541, then I reject the hoe. Okay, that's my rejection region. Right? What is my standardized test statistic? What did I find? I found T to be negative 1.765. Where does that fall with comparison to this negative 4.5 something? It falls right in here. I have a T equal to negative 1.765. So what does that mean? I'm in the non-rejection region. Okay, so since T is greater than the negative 4.541, we fail to reject H naught. I fail to reject H naught. How do I interpret this answer? There is not, why do I say is not? Because I failed to reject enough evidence at the alpha equal to 0.01 level of significance to reject. Why do I say reject? Because my claim was the hoe. The only thing I can do with the claim hoe is reject the hoe. If the claim had been the alternative hypothesis, the ha, I would support. So reject the claim that the mean battery life of an MP3 player is at least 30 hours. So there's not enough evidence to say reject the claim, okay, that they're actually lying. So there's not, even though I suspected they're lying, there's not enough evidence to say that they actually were lying. Okay, guys, I hope that that example makes sense, and there you can see the whole thing. All right, that's it.